Hey class. We're getting near the end of the semester. This is uh, the third to last lecture for the semester. The final one will be a review that'll be next Thursday. The one before that will be the last topics. I intend to go over some concepts that you should keep in mind in terms of securing your application. Um, so today is the last one for just general thought in the world of discrete math. So new concepts. I'm not really supposed to teach you anything new next week, so I'm going to get around that by teaching something that you don't necessarily need to know in the context of this course, but is good to know going forward. So for today's topic, I wanted to revisit decision trees and make it a bit more of an abstract concept, and then tie it into the concept of machine learning. So we'll see how far we get. It's very much theoretical. I won't be able to show you the demonstration of an application. I believe there are some examples that are out there. Next year, as is always the case, it's better to take it later, right? Because next year I'll be a little bit better. But hopefully you still got something out of this course, and it's not all. I wish I was in next year's class, but we'll see. Anyway, so it's Thanksgiving week, so you should be in full blow off mindset. All this work that you need to do, and definitely don't want to do it. Hopefully you're at home in your pajamas, in your jammies, and enjoying the day. So we'll call it Jammy Day, and you can enjoy the fact that this won't necessarily be on the exam. Let's take a look at what we've got. I wanted to revisit the sorting problem. Again, this always seems to be the example because it's something that's so readily understood. So whenever we wrote it the first time, we had this sort function. It takes in a number array, and it returns some variation of the number array. Either we've modified it directly, or we've created a new one, or something. We have our collection of numbers, and they're in some order, and they're not even necessarily consecutive. So we could do 10, 20, and 30. And then we just want to write it out. So numbers, what do we get whenever we run that? So it spits it out, okay. So let's have our sorted numbers. Okay, as far as we can tell, it looks like it's working. Let's try a different variation on that. It does not, in fact, spit it out correctly. Right? So when we were using merge sort, we defined it slightly differently. We had a merge method and a merge sort method. So we had merge, and this took in a collection of items. It had a start, a min, a medium, a midpoint, and an end index. And this is if we're sorting it in place. So then the second block start point is mid plus 1, And I'm really just translating what's in the notes for the recursive merge sort in C. And so then if the items mid less than or equal to items second block start, then we return. Okay. Otherwise, start less than or equal to mid and second block start. And we're following the rules of an algorithm here. And so we've all seen it before. So I don't want to get too caught up on the details. What I want you to think about is everywhere that you see an if statement, what's that actually doing? And in particular, would it be possible to remove the while statement, right? So we've discussed this in terms of decision trees. But the while it's flow control, the comparisons, the less than comparison that we've been discussing, is actually entirely contained in the if statement, and that's, we'll see that in just a second. Anywhere that there's an assignment. Alright, so these are the merges. Okay, yeah. And I guess we're... Oh, yeah, okay. Yeah, so this comparison, the if comparison, happens right here. Right? So then we pick and so forth. Okay, so then if we don't do that, and we follow the else block, we have the value, which we pull from the second block. Okay. So index or items were really is our container. It's both our source and our destination for these values. And it looks slightly different than the version we covered before because we're doing it in place. So we don't actually need two lists and merging them into a third. We have the second half of the list and the first half of the list. And if the first half is less than its corresponding member in the second half, then you don't have to do anything. So really the only action happens if is in the case that this item is actually smaller, so that this is not less than or equal to, which means that it's in fact greater than, right? So then we have to perform some swap. And so obviously that happens inside the else block. Okay. And already I'm kind of regretting this choice of doing the in place one because it kind of hides some of what's actually going on. So that's the merge function. And then the merge sort function, which is where we actually break it up recursively and then we call merge to fix it. So that accepts an items collection, a left index, and a right index. And again, this logic is associated to the in place, so that we're not creating a bunch of arrays, just to demonstrate that it is possible to do it without scaling up the memory. Okay, so we have our midpoint. And then again, we recursively call merge sort. we pass it the items, but now with the collection split between left and right. Okay, and that's it, right? So we're recursively calling this, and then eventually we'll get to a point where we've broken it up to where it's just a single item in each list, and we pass it into merge. And so merge does all of the heavy lifting of making sure that when they're zippered together, when these adjacent cells are zippered together, that it's always done in a sorted fashion. So let's see if that actually works. Oh, and I never returned the items, I guess. Oh, I didn't pass in a left index and a right index. Okay, so then we pass in the items. The left index is 0, and the right index is numbers.length -1. Oh, and it doesn't return anything. So what we actually want... Oh, and we can already see it. It is sorted here. So whenever we printed it out up here, it was sorting it in place. So that wasn't... So this wasn't really doing anything. Okay, so the sorting logic works. And you can see how we're using this loop and the if statements. We're making all of these recursive calls. But whenever we described the algorithmic runtime, we used a decision tree as the data structure to represent the logic that's happening and how many operations are necessary. And so now I want to unroll the loop for you. I want you to see this problem. If we didn't use an algorithm, then how could we specifically do it? And so we've already shown that this algorithm will solve the problem for any collection of integers that are passed in, or really any array or list or collection of objects where you can compare using some less than operator. But I want to show that there is a series of comparison operations that are taking place, and in fact you could solve the problem in that manner, but as you'll see, it's not a terribly efficient solution. Okay, so it's a series of comparisons, right? So let's start by comparing the first two numbers in the array. So we compare the item in place 0 with the item in place 1. Okay, and if 0 is less than 1, then those two are already sorted relative to each other. So then we have to compare the second item in our array, the one at index 1, with the last item in our array, the one at index 2. And if those are sorted, or if those are already if the item at index 1 is less than the item at index 2, then the array is already fully sorted. Alright, so in that case, the 0th item comes first, the 1 item comes second, and the 2 item comes last. Right? So it's already sorted, so we return a new array with items selected from that original array in the same order that they came in. Otherwise, well, we know that if this is not less than this one, well, then it's either then it's greater than or equal to, right? But at that point, we want to compare this item to the one in slot 0. And so we know that this one is greater than both this one and this one. And so that one will come last whenever we return our array. But then this one will, its position is determined by this comparison right here. So if the item at slot 0 is less than the item at slot 2, then this is the order. Otherwise, this is the order. Okay. Because we know from this first test that the item in slot 0 is less than the item in slot 1. So in all of our leaf nodes, all of our return statements, this one should come before this one. Right? This one should come before this one. 0 should come before 1. Right? So 0, 1, and 0, 1. So that's the case in all three of them. Okay, so the other case is where 0 is not less than 1, where the item in slot 0 is not less than the item in slot 1. So then we need to compare. We need to make the basically the same comparisons, except everywhere that we had a 1, we need to put 0, and everywhere that we had a 0, we need to put 1. Right. So if this is greater than or equal to this, then we know that this will come before it. And what we need to find out next is whether this item that was first in our list, the one in slot 0, is at the end of the list, or if it goes somewhere else. Right? So let's make that comparison. So 0 compared to 2. And if it's less than, then by this test, we know that 1 comes before 0, and by this test, we know that 0 comes before 2. So then this is our order. And if that's not the case, if this one precedes 0 and 1, well, we haven't compared the item in slot 2 to the item in slot 1 yet, so we need to do that now. And so if 1 is less than 2, then this is our order. And again, just swapping 0 and 1. Otherwise, 2 comes first, 1 comes second, and 0 comes last. Right? So you can see now that these are our final states. Right? So an array with 3 elements is going to have 3 factorial final states. Right? So 3 factorial is 6, and we have 1, 2, 3, 4, 5, 6. So 6 possible input orderings leads to 6 possible paths through our decision tree. And we don't actually return that because it's always returned from one of these others. Okay, so that's exactly what we claimed before, that we would have 6 leaves, and then the tree height would be determined by the log base 2 of that n factorial. Right? So you can see it now unrolled. So this is what we were doing algorithmically, and this is what we're doing if we unroll it. So does it work? Did we did we just accomplish anything? Well, let's see. So if we run it now, we see that this was the input and this is the output. So does it work for any other combination? Sure, let's move 30 to the middle. Again, it was properly sorted. Let's move 30 to the end. Again, it's properly sorted. Let's try this. Still properly sorted. Again. Again. Okay, so we were actually able to enumerate every possible path for an array of size 3. So, so is this an algorithm? Well, no, most definitely not. Right? Because if we tack on some number at the end that should come first in our collection, this sort function is completely blind to it. It's only looking for those first 3 array elements. So if we run this, we have an input of size 4 and an output of size 3. Now, what it spits out is sorted, but it's very limited. Whereas this, our algorithmic approach, the one that uses recursive method calls and loops and these comparisons of varying index, that solves the sorting problem. This only handles a very specific subset. Yet it does it in in a very straightforward way. You can see exactly every comparison that's made, and it's very obvious that that there's no waste to it. So if you can restrict the input to just arrays of size 3, or you could do this with size 4 and so forth, then you could still make this guarantee of some algorithmically correct approach. Granted, it has to be exactly that size. It won't work for anything that's less than whatever you've hard-coded, and it won't work for an array that's larger than what you've hard-coded. So this would not work on any sized array other than 3, right? If you only have 2 items, then you'll get an index out of bounds error, or you'll get undefined in JavaScript. Or if you have anything that's larger, so 4, 5, 6 elements, then everything after index 2 is just going to be completely ignored. So it's very, very limited in what it can consider, but for what it's coded to do, it is correct. So that's perfectly achievable. And so this decision tree, the hard-coded variant of what we've made here, is correct, and it's still bound by those same considerations that we had whenever we were discussing algorithmic runtime for merge sort and so forth, in that you can't guarantee a correct output in fewer than the log of the height of your decision tree, where the height is determined by the number of leaf nodes, and it's log base 2 because these are the decisions. Right? So even though we're really only 2 levels deep, this comparison does have to take place before this one. Right? So we have 1, 2, 3 comparisons at its maximum height, and the same thing over here, that 1 and then 2, 3 over here. So you can't do it for this in fewer than 3 comparisons. And having seen this, you can understand why. Like it has to take place. You have to support each of these final return states for the given input array. Okay, so why? Okay, so why did I bother to show you that if it's so limiting? If it holds very limited promise? Okay, well, I wanted you to consider these problems in a new light. I wanted you to rethink these algorithms. So, okay, what we've considered runtime complexity in terms of how these algorithms scale in terms of performance with a variation of input. Now I want you to consider how we program these solutions, or how we can arrive at these solutions when we fix the input size. And when would that ever be the case? Okay, so now we get to discuss machine learning. So imagine a grid. So imagine a pixel grid of 32 by 32 black and white pixels. So then the number of the number of pixels in the grid is 32 times 32. This is 2 to the 5, this is 2 to the 5, so their product is going to be 2 to the 10. And then each one of these pixels will be grayscale. So you can do it with a different encoding, but you lose a bit of information. And faxes actually used to be encoded that way. So it's 0 if it's black, it's 1 if it's white, or you can invert it as long as the sender agrees with the receiver. But even if it doesn't, then you're just flipping black and white. You just don't want to waste black ink, right? But anyway, that proved to be effective, but ugly, right? So it's a little nicer to have a grayscale image, and so the representation that just became common is to give it a byte of grayscale coloring. So you have 256 distinct shades, ranging from 0, which is all black, to 255, which is all white. And so you can consider it as being in the range of 0 to 255, or being in the range of 0 to 1 by dividing that in 255. So you have something that can be represented by 1 byte or by a double. It's whatever's convenient, but you can just see that there are these gradations of black and white. Anyway, but now we can actually count how many possible inputs there are, or how many possible states there are for this 32 by 32 grid. Well, each one of these 1,224 pixels has a possible 256 distinct states. So it's the product rule again, right? So so then we end up with 2 to the 18 possible states. So that's going to be on the order of like 256,000 possible states, or something in that neighborhood. Okay. So then this grid is capable of representing that many distinct possible inputs. So we have the input space. What do we want to consider as our output space? Okay, so imagine you're using this 32 by 32 grid for some characters. So it could be 0, 1, right? Any digit between 0 and 9. You could also consider the alphabet. Right? A, Z, whatever, all of those different variations. But regardless of what you're putting in this grid, the input space doesn't change at all. There are only 256,000 possible inputs for this 32 by 32 grid, which it's not an impossible amount. Like you could iterate that. You could consider every one of those possible inputs, and that's not so bad. It's something that you can deal with, and so think of it as being exactly that. Right? So if we limit our discussion to just the digits between 0 and 9, then what we're working with is 218 or 2 to the 18, and you can think of this. This is just one possibility for the number 9, and so other people are going to write it differently, and it'll scan in differently. And then also it can be shifted around a bit as well, and it's still the same number, like even if you moved it up one row of pixels and so forth. And so in terms of creating all of the branches by hand, like we now end up with an awful lot of combinations to have to deal with. So this problem, you could do it with that series of if and if else statements that that we were doing whenever we were sorting the numbers. So if this pixel is white, and this pixel is white, and this pixel is white, and so forth, and the entire first row and so forth, and handling these cases one by one, you could actually hard code that. The input space doesn't really change at all. But you're going to deal with massive depression in your development department if you're asking them to code these scenarios one by one. So there's got to be another way, and so algorithmically you could attempt to do like, okay, well, if the curves are within some variance of error tolerance or whatever, and you have all of these strokes or whatever, you could try that, but that's also going to be you're just going to miss a lot of cases, and it's not going to bear fruit in proportion to the amount of time spent on the problem. So then how do you solve this problem? Okay, so this is the type of problem that that machine learning is really good for. So we've restricted the input space. The output space, well, let's get back to that, and then we'll talk about the problem going forward. Okay, so we have some measure of these final of these inputs. Right, so mu for measure, right? That equate to 0. So if we're just considering the digits, then some of them are going to be 0. Some of them are going to be 1. Two, 3, all the way up to 9. And then the rest of them, the balance, is going to be none of the above. It's going to be the empty set. So there's 11 possible final categories, but as we were discussing these problems, like that isn't necessarily the number of leaf nodes, right? Like because we're considering this as a series of if-else statements, and it falls into something. And so I think the correct way to view this is that these categories are just part of a final state, so that we have 11 categories and the input, right? So that we now have this one-to-one relationship. So the input will fall into exactly one of these 11 categories. So there's no overlap. They're disjoint sets. But you consider whatever input maps to that final category, that final state, and then you have the same number of leaf nodes as you had for inputs. Okay, so then what does this tell us in terms of how to arrive at that final state and how to create a program capable of categorizing this to one of those 2 to the 18 final states with 11 possible categories associated to that final state? How do we train that? How do we use machine learning to do that? Okay, so let's return to what we understand about decision trees. So we know that in order to support this many leaf nodes for a given input, so this many leaf nodes, because we've decided to pair it in these disjoint sets, so that there are this many final states, then we know that our decision tree, in order to support that final state, has to have a tree height equal to the log of this, right? Log base 2 of this. So that, log base 2 of 2 to the 18 is just 18. So we need 18 levels of comparison in order to do this. But what does that comparison look like? That's not exactly clear. Okay, so now let's jump into it. And so again, I don't have a working example to prove my case, but I'm going to make this argument based on what we've already covered, and it will either help you or dramatically hinder you. But I feel pretty confident in what I'm sharing and what I'm discussing. But this is the idea behind neural nets. Okay. Okay, so we had that 32 by 32 is equal to 2 to the 10. So we have two to the n, or 2 to the 10 input parameters. So each one of the pixels would be considered an input parameter. And then each one of these inputs has one of 256 possible values. And then, so this is our input space. And then something happens. Right? So something considers all of this, some magic happens that we haven't really discussed yet. And then it maps to something between 0 and 9, or the empty set, or none of the above. So if our 32 by 32 grid was just all white or all black, or any of those variants of gray in between, or just scribbles or anything, then it's the field. It's something that isn't one of these distinct 10 categories that we're actually searching for. So we would actually expect this to represent the largest number of final states. So don't forget the empty set whenever you're writing your machine learning programs. Otherwise, your training data is somewhat incomplete. Like, it needs to recognize garbage and categorize it as such, right? Or if it's part of a larger decision matrix, then it would be considered as something else, right? So if it's not a number, then is it a letter? And if it's not a Latin letter, then is it a Hindi letter, or is it part of simplified Chinese, or Korean alphabet, or something, right? And so so this is just the else block, so we have to account for it. Okay, so then what happens here? What happens in the black box? Well, the way that it's represented is that there are these hidden layers, and in fact, whenever we make our decision tree argument, then these are the decisions. These are the comparisons, and so forth. And we know from the log of the possible final output states that there has to be at least 18 such decisions taking place. And then it's so we know that there are comparisons taking place, but how do we represent that? And is it these Boolean comparisons, like the if-else statements and so forth? And that's not actually the way that they do these. That's not the way that they train these programs and these algorithms to account for this problem. They actually treat them as polynomials, which I think is rather clever. And so this turns out to have a series of layers, essentially. So that you have so you have your first layer, or your zero layer, however you want to index, your subsequent layer, and then up to that final layer. And from our decision tree argument, you should have, if you want to solve this deterministically, if you want something that's actually capable of considering every possible input and mapping it correctly to one of the 11 possible categories, then you're going to need no fewer than 18 layers. And then the neurons are the polynomial that essentially represents that layer. And so okay, so you have some collection of neurons here, and they do a thing. They take in the 256 possible values for each one of these 1,224 input pixels, and then it crunches it into this a vertex, or a vector. It crunches it into a vector with some number of items in it, and then that feeds in to the next polynomial, which is again another vector with some number of items in it. And the output from this feeds into some final polynomial, and that final polynomial is what essentially makes our decision. It spits out some a vector that is actually something that we can recognize. So this final polynomial's output would be an 11-item vector, and then ideally, so it'll have some confidence that indicates, it's, 5% chance that it's this number, 10% chance it's this number. But ideally, it would be 100% it's one of these numbers, or 100% it's not a number. Okay? So then the output of this vector will be it'll be 11 items, and it'll have a 1 at the slot associated to that output number. So that this has 0 error, right? If it's correct, it's completely correct for all inputs that equate to 1, and then it only switches in the case that it's some different number, or that it's gibberish. Right? So we know what the output of this one is. Well, in order to achieve that, then the number of elements in that vector, I believe, should correspond to the number of final output states. Or in the case that you're dealing with something where the input is smaller than the final output states, then you're still bound by that tree height argument. So the number of layers is determined by the final output states, but the number of neurons per layer, I believe, is going to be the minimum of either the number of input parameters or the number of outputs in your final state vector. So in this case, if that if that hypothesis is correct, then in order to have a chance to correctly solve this, to solve it for all of the 2 to the 18 possible inputs, then you would need something that is 11 neurons by 18 layers. And so, well, if these are polynomials, and we have something that we can consider correct, then we can write a cost function, and that cost function is the amount of error. So let's assume that this was passed in, and it should be identified as a 1. Like we would expect any person that was looking at it to categorize it as a 1. So we know what the final state should be. So if it outputs if it outputs something like that, then we can use something like a root a root mean squared, or just the sum of the differences squared, right? So okay, so then the error for that input is this measured quantity. And you're dealing with a set, a collection of inputs. So then that collection will have some total error. And the values that you can tweak along the way are these polynomials here, right? So it'll be every one of these, everything from the previous state feeds into everything, or from the previous layer, right, starting with the input, feeds into the everything for the next day. So that every one of these pixels is considered in this first neuron, and the same is true in the second, and so forth. So for each of these 11 neurons in layer 0, and then every one of those 11 neurons, the output of it is considered in this each one of these neurons in the second one. Okay, and so forth, right? So that's the net part, right? So that everything is considered together, and then it just continues to feed into the next layer, and so you have something that is this collection of 18 times 11 polynomial coefficients, and it's also possible to consider some bias as well, so that you're you're making it harder in certain cases for something else. So you would have the same number of potential biases as well. So this is the matrix that you're tuning, and this is how we measure cost. And so the idea is to minimize this total error so that everything is correctly categorized at the end with 100% confidence. And again, the input space is only 2 to the 18. Well, we can count to 1,000,000 in less than a second, so it's not entirely impossible to just exhaust the input space. The problem is that with training, you already need to know the answer so that you can measure this amount of error. And so they have training data that's available, and you would use that, and it would already have the image, and then it would also have the answer available to it as well, so that you can continue to go over and over again. So then, well, if we have these parameters that we can measure, and we have some output scalar value, so this isn't a vector, this is just a single real number, then in that case you can use the gradient. So you have 11 times 18 parameters, possibly times 2 as well if you're using biases as well, and then you're tuning them, right? So each one of these 2 times 11, so 22 times 18 variables can be tuned, ever so slightly, and then as you move each one of them, it's going to have some difference in output value, and so that's exactly what the gradient is. So you have some scalar valued function, which is controlled and tuned by some number of parameters, and then you measure the change in the scalar valued function with the small change in those parameters, and the gradient of that will be the path of steepest ascent, but you're trying to minimize the amount of error, so you actually would go in the opposite direction of the vector that is generated by that gradient. And so that's the idea behind machine learning and neural nets, and the types of problems that they can solve, and how they relate back to the decision trees that we discussed before. So that concept does still apply even in machine learning situations, but the trick is to restrict the input space to a very finite scenario, so that you can actually deal with it. Okay, so that's it. Again, it'll be better next year, so it's a shame that you took the course this year. But that's the idea behind it. We'll go into our security review on Tuesday, and then next Thursday will be the overall course review. But I do have 2 very special guests, at least in my eyes, and so they really wanted to come in and wish the class a happy Thanksgiving, and so we'll do that, and then we'll dismiss for the break. Okay, girls.
Yeah.
Oh.
Happy Thanksgiving.
Yeah. So happy Thanksgiving, class. From me and my girls, and I hope you have a great break.
You and you and you. Bye.